Good morning, boys and girls. Here we go. We are jumping right into related rates. This is going to be an action-packed lesson, so I'm going to just get going and get after it here. All right. As you can see, when we do a related rates problem, it is a word problem. First off, you want to read this thing several times. So I would say pause this. Read it 3 or 4 times to yourself. Really try to understand what's going on before we jump into this. That way you understand what I'm about to do. Once you have read the problem a few times and you feel like you got a pretty good grasp of it, the next thing you're going to want to do is to do what I did and draw yourself a picture of the scenario, okay? That'll help you wrap your head around what's going on. When you do this, couple things when you draw your picture. Artist 3 is not super important. Just get something that resembles what's happening. But you're going to want to label the things in your picture. And when you label the stuff, when you label your picture, a good general rule to follow is only put numbers on your picture that are not changing. Okay? So in this problem, we have a 25-foot ladder is leaning against the wall. Okay? My ladder's 25 feet. Is that changing? No. A ladder's always going to be, or this ladder is always going to be 25 feet. So because it's not changing, I can put that value on my picture. Okay? It is sliding away from the base of the wall. I'll come back and I'll talk about what that rate represents here in a second. And the top of the ladder is moving down the wall. So I kind of like to do these arrows to kind of illustrate this. This distance here, as the ladder is sliding away, though, that is changing. Because that's changing, I need a variable in its place, so I'm going to call it x. Okay? As the ladder moves down the wall, again, that distance is changing. So I need a variable to represent that, and I'm going to call that y. Okay? The rate at which this is changing is the change in x over time, right? Delta x over time, or better known in math as dx dt. Okay? That rate that we're going to find is known as dx dt. And the rate that's moving down the wall is the rate at which y is changing, so dy dt. Okay? As I'm labeling my picture, I also like to come into the side here, and I like to write down the things that I know. So in the problem, it tells me that dx dt is 15 feet per second. Okay? How fast is the top of the ladder moving down the wall? So we're going to be looking for dy dt. Right? I want to know how fast it's moving down the wall when the top of the ladder is at 7 feet. So when y is 7. Now again, that y is changing, so don't put 7 on your picture because that's a changing value. But I can put it over here on the side when I'm writing out all my information that y is going to be equal to 7 or 7 feet. Okay? That's my first step. Read the problem, draw a picture, write down what we know. Next, what we need to do is we need to write an equation that relates all of our information. So in this case, if I'm looking at my picture, we have a right triangle here, right? Hopefully, if our wall is well built. So maybe I could use x squared plus y squared is going to equal 25 squared. Okay, or c squared or z squared, whatever you want to call that. Again, going back, when you're setting up your equation, if something is changing, you need to plug the variable in. If it's staying consistent, like in this case, the ladder is consistent, I can plug the number into my equation right there, just like that. All right? Once you write your equation, you now are going to take the derivative of this equation implicitly with respect to time. Okay? We have already talked about taking the derivative of like an equation like this, but with respect to x. And so we had 2x dx plus 2y dy dx. We are now going to take the derivative of this, though, with respect to time. So when I do that, the derivative of x squared is still 2x, but now I got to tell people I just took the derivative of x with respect to time, so dx dt, and that's how I get that rate. Plus 2y dy dt. I just took the derivative of y with respect to t. Okay? And then the derivative of 25 squared is 625, but the derivative of any constant is 0, so that is 0. All right? So now I've got my related rates. Oh, stop. I meant to show you guys a picture that illustrates this. Give me 1 second. Sorry, I got so excited doing the math that I forgot about this animation that I wanted to share with you. Okay, so we'll get back to the math there in a second. But here's our little animation. It's on GeoGebra.com if you want to do this. If you just search GeoGebra related rates, I think this is one of the first things. It's a very common problem that will pop up at this little animation. But it's our ladder that we get leaning against the wall. This ladder is of a different length, and we're going to have it fall at different speeds. But just so you, again, I think it helps to get an idea of what's happening in the beginning with these, where you can kind of see these related rates. Okay? Because you might think when you kick the ladder, as it goes out at a constant speed here, you would think it'd fall down, the top would fall down at the same rate. But if you watch when I kick this ladder, that is not necessarily true. It should start in a second. Hopefully this is not too much for it to handle. I'm going to pause it while it gets going, then we'll turn it back on. Okay, so I've kicked the ladder, now I've got this thing working, and so now the ladder is falling down the side of the wall, right? You can see that the bottom of the ladder is moving at a constant speed. In this case, it's moving at 3 feet per second. And you can see the top of the ladder that was not moving at a constant speed. At the very top, it moves very, very slowly, but as the ladder falls, it starts to speed up really fast. Hence that weird little feeling you get when you start, when you're on a ladder and you start to fall. You get to like, oh God, and then all of a sudden it's over just like that, right? I think it could be explained mathematically here with this. It starts very, very slow, but then at the very end, boom, you're on the ground before you know it, right? And so I can play with the speed. If I, speed it up, you can see a little bit faster here, but same idea. The bottom's moving at a constant speed, and the top speed changes, but it's the rate at which it's moving is related to how fast, through the length of the ladder, how fast the bottom is going. Okay? So again, what we are going to try to do here with us is we are going to try to, we are trying to find how fast is it moving right about here. When when the top of the ladder was at 7 feet, how fast is our ladder moving? All right. So now let's go back, now that we kind of got an idea, let's go back to our original problem and we'll connect. All right, so now kind of recapturing where we were at, we had the picture of our ladder. We have an idea of what it looked like as it's falling down the wall. We wrote an equation that related all of our lengths, right? And then we took the derivative of that equation with respect to time so that we have our related rates equation. We can see how these things mix with each other. We said we are looking for dy dt. So I can start plugging in things that I know. I don't know x, right? We didn't write that down. I'm going to have to go back and find that in a second. But we know that the ladder is moving at 15 feet per second, plus, that was our dx dt, plus 2. We know the y. Now, once you take the derivative, then you can plug in things that are changing. So now I can plug in my 7, and I'm looking for dy dt, and I know this whole thing equals 0. So now really to find dy dt, I guess all I need to do is I got to find that x value. And so to find that x value, I really care about where that x value is when y is 7, right? So I can actually go and use, set up a little triangle, and I can go and solve for x when y is 7. And that's the value I want to plug in, right at that one instant moment, that, that little, we're going to find it. Okay, so to do this, again, we would use the Pythag again, x squared plus 7 squared equals 25. And you could go through that work if you wanted to, or, I did this problem earlier today getting ready for this lesson, or you could recognize that this is a Pythagorean triple, and you're going to end up with a x is 24, a 7, 24, 25 triangle. Okay? Do the math, you'll get to that, or just trust me, x is 24. Once you get x is 24, then you can plug that in here as well. And then now I'm ready to go ahead and solve this equation. 2 times 15 is 30 times 24 is something like 720 plus 14 dy dt equals 0. Solve for dy dt and you will get that is going to equal negative 720 over 14, where if you reduce that, that's negative 360 over 7. When you're done, always think about your units. Y was being measured in feet. Our time was being measured in seconds. So this is negative 360 over 7 feet per second. All right? Also, think about your answer. Okay? Does that answer make sense? And yes, because the ladder is falling down, right, it has a direction, it makes sense that my velocity of the ladder is negative, right, or the rate of the ladder is negative. Okay, going to move on here. All right, here we go, our next related rates example. Again, word problem, read it once, twice, 3 times before you even put pencil to paper, okay? Make sure you have an understanding of what's going on. So again, I'm going to say pause the video and give this thing a little read. And then again, once you're done, draw yourself a picture. It doesn't have to be great, just something to kind of get the idea across, all right? Again, what we're going to do, I've got another illustration for this one here that we can use to kind of look at, to kind of understand what's happening. Looking at this one, we have a rocket that's rising vertically at a rate of 5,400 miles per hour. We'll fill things in here in a second. The observer standing on the ground is 20 miles away from the rocket's launch point. How fast in radians per second is the angle of elevation between the ground and the observer's line of sight, increasing when the rocket is at an elevation of 40 miles. All right, so let's look at this example illustration to see what's kind of going on. Again, different numbers in this thing, and different picture a little bit. We got a satellite instead of a person, but kind of same idea. We've got this rocket taking off. The satellite is going to watch it just like the person would watch it as the rocket takes off. Sorry, not sure if you saw that or not, but my battery started running low in the middle of the thing, and I didn't want it to die in the middle of our video. Anyway, the rocket's going to take off, and we're going to try to track it with the satellite. All right, so here we go. All right. Okay, here's the rocket taking off. You can see that the angle starts kind of quickly to begin with, but then as it gets higher and higher and higher, the rate of the angle is changing, is getting slower and slower and slower, even though the rocket is taking off at a constant speed. Okay? Very fast angle is changing, and then very slowly, right? Those numbers start to change slower and slower the higher and higher it gets. Okay, so that's, again, the related rate we're kind of dealing with on this problem here. Okay, so reading through this problem again here one more time. The rocket is rising vertically. It's rising at a rate of 5,400 miles per hour. Again, because that's going up, that is our dy dt, right? The rate at which it's going up, dy dt, is 5,400 miles per hour. An observer on the ground is standing 20 miles away from the rocket's launch point. This is not changing, right? The distance from my observer to the y was changing, so I should label y, but the distance from the person to the rocket's not changing, so I can put 20 right on my picture, right? How fast in radians per second is the angle of elevation between the line of sight and the rocket when it's at an elevation of 40 miles. So I want it when y is 40. I'm looking for how fast the angle is changing, theta. So I'm looking for d theta dt in radians per second. Okay, 40 miles. So that's the information that I'm dealing with right here. All right. Now, once you got all this information down, we kind of understand what's happening with this problem. I need to write an equation that relates all this stuff. So again, I've got a triangle, right? We had that right triangle with y's and the 20 and the theta. Oh, maybe this relationship is tangent of theta is the opposite over the adjacent. So that might be something that relates everything here. Okay. Once you have your equation, we can go ahead and take the derivative of this with respect to time. Now, what I probably would do with this equation before I took the derivative, even though I could make this like 1 over 20y, I think it's easiest oftentimes to multiply both sides by 20, and we're really going to play around with the equation of 20 tan theta equals y. And I've got about 1 minute left on this video, so I think I'm going to stop right here. This is obviously one of our more challenging sections, hence why I generally teach this one in class, and this is just for you to come back and look at. But I'm going to pause this right here, and you will pick this up on part 2 of related rates. See you real soon, boys and girls.